Okay, so I'm going to actually record this. So we now have covered Chapter 13, all the new material, and your final exam is upon you. Many of you have scheduled your final exam and examity, and some still, I think a few of you still need to. But one challenge students have in Chapter 13 is they're given a problem, and they have to decide what approach to use. Okay, and so what I've done here is I prepared a document. I basically copied different pages of the book and took out problems and pasted the problems with tape and whiteout, used whiteout on, and there's 6 different situations on this page. And so you're not going to actually be, I mean, for this exercise, it's not working these out that I'm asking you to do. It's for each scenario, what theorem or approach applies. Okay, and again, you are able to download this document, so you might want to do that, and then you could then blow it up on your, like, magnify it on your screen. I can magnify it here. Now, the next page, the second page you see here, has it's the formula sheet. Remember, I said I was going to give you a formula sheet for your final exam with Chapter 13 type of formulas, and this is the one. And this time, what I've done is I've numbered the different formulas and approaches 1 through 7. Now, number 7 is other formula, okay? Because this is really, these are some formulas from Chapter 13. And then, the question is that, hey, could there be another formula you might need use? So what I'd like you to do, I want to give you about 15 minutes here. And you're welcome to, work with each other here in the room, using the chat or as you wish. I want you to look at each scenario here and then identify what approach applies. So like the first scenario, it says evaluate that integral, and C is oriented clockwise as viewed from above, and there's the vector function, there's the vector field, a 3-dimensional vector field, and the curve C is a triangle with those vertices. If, for instance, you were to have this problem on your final exam, okay, what approach would you use? Is there an approach here on the formula sheet for Chapter 13 formulas that you should use? So, like, for instance, if you think number 4, Green's theorem, is the right choice, then for the first scenario, put a number 4 next to the first scenario. If you don't think Green's theorem would work here, then pick another one. Pick another choice. Okay, does this make sense, this exercise, what I'm asking you to do? Okay, Yeva, you're comfortable? Are there any questions at all? Okay, Matthew's good. Okay, all right. So this now, take about, I'm going to actually give you, I guess, till 6:25. I'm going to give you 17 minutes to match each scenario with one of the numbered formulas, 1 through 7. 7 just means other formula, okay? All right, so I'm going to have you do that, and then at 6:25 p.m. I will go over the answers with you, and let's see how many you get right. Hopefully you'll get many right, and then after we're done with this exercise, which is to help you help review for Chapter 13. Then we will proceed on and talk about MATLAB assignments, the final exam, and so forth. Okay, are there any questions before you go off to work here on this exercise? Give me a thumbs up if you're comfortable. Okay, Yeva's good. Norina's good. Okay. Okay, all right. Logan's good. Wonderful. So I think this will be very helpful for you, this exercise. This is not busy work. I don't give busy work. This is to help you get prepared for your final exam. You know, chapter 13 is very important. Okay, I'm going to let you work, and I'll meet back with you in 15 minutes. And I will leave the recording on here. Okay, so I'm back, about 4 more minutes here. Hopefully you're making some progress. Okay, another minute or so. I sent a couple of messages to a couple of students. Uh, so be sure to check your your chat message, chat messages. All right. All right, so let's take a look here. One moment. Okay, so the in this scenario A for this exercise, you are computing, and I'm going to try to highlight it the best I can here. You are computing this line integral, right? What does that line integral represent? When you see that in homework or on the exam, what physically are you computing? So for the first scenario, they want you to evaluate this line integral. What does that mean in terms of applications? Are we finding work or are we finding flux? What kind of integral is that? Does that stand for work or flux? Yeah, it actually stands for work. It actually stands for work. And what does that mean? Well, so there is a vector field here. Here's this vector field, and I appreciate all honest responses. It's good to participate. Here's this vector field. The vector field acts in three-dimensional space. The particle C moves according to this triangular path with those vertices. We want to know if the vector field, the net effect of the vector field is to help the particle move along that triangular path or to hinder it, and work will be positive or negative respectively. Now, in the choices that you have, okay, if you look here, students tend to naturally be attracted to Green's theorem because of course, in Green's theorem here, the left-hand side, the sum of those line integrals with respect to, one with respect to x, one with respect to y, is equivalent to this work integral. But Green's theorem cannot be used for scenario A. For scenario A, choice 4 would not be correct. Okay, can anybody tell me why? Why is Green's theorem not going to work for choice A? Well, Norina, it doesn't have to do with a conservative vector field. Green's theorem allows you to find the work. The vector field does not have to be conservative for Green's theorem. Good try. There's something else about Green's theorem that should be noticeable when you look at the theorem. When you look at Green's theorem, something important about it that would mean you cannot apply it to the first scenario. The vector field F, right, is equal to P, some function P of xi, of x and y times the vector I, plus some function Q some component Q of x, y, j. So for Green's theorem, that's your vector field. Okay, good, Jacob, good. That is a two-dimensional vector field for Green's theorem. But in scenario A, here, you have a three-dimensional vector field. So you cannot apply Green's theorem to find the work. Very good. Well, you cannot apply Green's theorem because the vector field F in scenario A is a three-dimensional vector field. Okay, so what choice is going to be then the right choice? That's right, Norina, choice 5. Choice 5, because in choice 5, Stokes' theorem, that allows you to find the work that a particle does, that a vector field does in moving a particle along a closed path. Now, I mentioned too, class, I should mention this. This, in scenario A, we do recognize that this is a closed path, this triangle, right? It's a closed path. So to find work, Green's theorem is for closed paths in two-dimensional space, but Stokes' theorem allows you to find the work that a vector field does in moving a particle once around a closed path in three-dimensional space. Okay, so Green's theorem is C is closed, path is closed, and the vector field is two-dimensional. Stokes' theorem, the path C is a closed path, but Stokes' theorem allows for the vector field to equal, P times I plus Q times J plus R times K. Okay, does that make sense? Green's theorem is two-dimensional. It's for two-dimensional closed paths. Stokes' theorem is for three-dimensional closed paths. So we have to use choice 5. I'm going to go kind of slow here. I want to make sure you're understanding. I want to make sure that that you're comfortable. Give me a thumbs up if you're feeling good. Wonderful, wonderful. Okay. Thank you, everybody. All right, well, let's put choice 5 then here. Okay, that takes care of the first scenario. Now, second scenario, B, says find the work done by the force field on a particle that moves once around the circle oriented in the counterclockwise direction. Can we use Green's theorem for B? We do have a closed curve, a circle. Can we use Green's theorem on it? Yes. Why, Logan? Good. It's a two-dimensional vector field. That's right. So you're going to use Green's theorem. Okay. Well, let's go on here. Let's go on. Scenario C, they want you to calculate the surface integral, okay, well, they're writing it this way. This is really a flux integral, right? A flux integral is a surface integral. They want you to calculate the flux of the vector field across the surface S. S is the surface of a box bounded by these coordinate planes. Okay, so it's a flux integral. So you're not going to be using Green's theorem or Stokes' theorem for that. We have to look at our other choices. We got to look at choices where we need to find flux. So this box has how many sides to it in part C, or in scenario C? The box has how many sides? Six sides. That's right, Norina. So if we were to find the flux across this box, we would have to, one way is to compute to find the parameterization for each side of the box, and then find the flux rate through each side of the box. But this box, you notice the box is it's a surface that's closed. It's a closed surface, right? It's a closed surface. So of the choices here, what choice would be the choice to find the flux across a closed surface? This surface S encloses a brick, right? A solid. It's a closed surface. Which of the theorems would be the right one to use? Good, Jacob. Divergence theorem. Absolutely. That's section 13.8. Divergence theorem. You could compute the flux across each of the six sides. You'd have to get the parameterization for each of the six sides of the box, and then add up the flux rates. But it's easier just to use the divergence theorem. Okay, please let me know if you have any questions. So for part C, best choice is choice 6. Ooh, excuse me. Okay. Okay, now for D, scenario D, they are asking us to find the work, okay, the work that the vector field does in moving the particle along its path. And the path C consists of the curve sine of x from 0, 0 to pi 0. The vector field F in D is a two-dimensional vector field. Can we use Green's theorem for this scenario D? Can we use Green's theorem? Green's theorem is for two-dimensional vector fields. Can we use Green's theorem for scenario D? Logan thinks we can. Does anybody feel differently? What kind of curve, if you use Green's theorem, what kind of curve, what kind of this curve C, the space curve for Green's theorem, what property does it have to have? That's right, Logan. It has to be closed. Well, now if you look at this scenario D, okay, is the space curve C, is that a closed space curve? It is not. Good. So you can't use Green's theorem to find the work. And you can't use Stokes' theorem. You can't use Stokes' theorem because this is not a three-dimensional vector field. And also, Stokes' theorem is for closed curves. Closed curves. Right? And the closed curve is the boundary for a surface for Stokes' theorem. For D, you're just going to have to do this the old-fashioned way. You're going to have to use another formula. And the formula that you would have to use would be the definition of the work. Hold on here. Okay, remember this? When we first studied section 13.2, when we learned about line integrals, and then we learned how line integral can represent the work that a force field, a vector field does in moving a particle along its path, the definition of that work integral was given here. And this definition works all the time, right? You don't need, and in fact, since you can't use the Green's theorem or Stokes' theorem for this scenario D, you're going to have to use the definition of the work integral. So that would be choice 7, other formula. Give me a thumbs up if you're feeling good so far. Good. Norina's good. Yeva's good. Christopher's good. Logan's good. All right. Wonderful. Wonderful. Okay. Now, choice scenario E. What did you put for your answer on that? For scenario E? Good, Simon. What do you think is the best choice of the 7 choices, 1 through 7 here? What is the best choice you think for this scenario E? Scenario E, they give up. Okay. Well, you could do a line integral, but I like Norina's idea about Formula 1, the fundamental theorem of line integrals. So this is point P to point Q. Okay, the path goes from point P to point Q. You notice they're not even describing the path. Is it a line segment? Is it a an arc? I mean, in order to use formula like Formula 7 here, you have to know what R of T is. You have to know what R of T is. But here in part E, they're not telling you. That means that they don't care how you get from point P, if you think about, let me just think about your space curve here, point P to Q. They don't care how you get there. In other words, it appears that you have independence of path for this part E. And also, so that tells you then what kind of vector field is F. What kind of vector field is F? If going from point P to Q, the work that the force field does in moving the point from P to Q, it doesn't matter what path you go. What kind of vector field would vector field F be? Well, okay, independence of path means vector field F is, by the way, if I take the partial derivative of P with respect to Y, we're going to get 3/2 times 2 times Y to the 1/2. Right, Norita, conservative. That's 3 times the square root of Y. And the partial derivative of Q with respect to X would just be 3 root Y. Well, this means then for part E, that the partial derivative of P with respect to Y, derivative of Q with respect to X. So this means that the vector field F, okay, for this scenario E, it is conservative. It is conservative. Conservative. And so you're going to want to use Formula 1, the fundamental theorem of line integrals, to find sorry, my little messy here. I like things to look good. Does that make sense? It doesn't mean for scenario E that you can't use 7, this line integral formula. It doesn't mean you can't use that, but you can, since the vector field F here is a conservative vector field in scenario E, you can go ahead and you have a conservative vector field, so you can use the fundamental theorem of line integrals. So you can try to find the potential function, right? A potential function for that vector field, and then use the fundamental theorem of line integrals. So, right? It's helpful to keep an eye out for that kind of thing. Okay, on this exam, final exam, you're going to be encountered with all kinds of different scenarios, and it'll be helpful if you have a clear idea of what theorem to use and when. Okay, for chapter 13 type problems. Okay, let's look at now scenario F. So for E, we're using for scenario E, it's fundamental theorem of line integrals, choice 1, that you want to use. Just looking things over here. Okay, so for F here, all right, what kind of integral does this integral represent? When you see a double integral of vector field F dot ds, where vector S is in bold, what does that stand for? It doesn't stand for work. It's not a work integral. It is and they're giving you kind of a clue in the paragraph there. Yeah, it's flux integral. It's a flux integral. That's right, Norita. So you see, all right. So let's see here on the next page, which integrals are flux integrals. Well, definition 3 is flux integral, right? And divergence theorem, choice 6, also allows you to compute a flux integral. But for divergence theorem, formula 6, the surface S at which you're finding the flux rate across, it has to be a closed surface. So the question is, do we have a closed surface in this scenario F? Scenario F, okay, evaluate the flux across surface S, and surface S is the part of the paraboloid that lies above this square and has upward orientation. So is surface S a closed surface or is it an open surface? In scenario F. It's a part of a paraboloid that lies above the square. Scenario F. Does the surface S include, so you got the paraboloid, okay, and it comes down. It's like a bowl coming down from the point 0, 0, 4. And but is it a closed surface in scenario F? That's a yes or no question. That's right, Norina. It's an open surface. It's not closed. It's not closed. Now, when we talked about the divergence theorem, we did a problem where we had the union of two surfaces. One was a paraboloid, and the other then was a disk. At the bottom, or on this, I guess the side of it, like the paraboloid opened to the right, and it touched then the disk. Then was like the surface opened up to the right until it touched the disk. So essentially, the disk and the surface together, sorry, the disk and the paraboloid together was a closed surface. But for F, you don't have a closed surface. So you're going to have to use the definition of flux to get for F, for scenario F. So that's going to be formula 3. Can't use divergence theorem on that. So that means then for the flux, to use formula 3, right, you have to be able to figure out the vector function of two parameters. It could be u and v, it could be x and y, it could be, theta and phi, whatever. But you have to find that vector function of two variables. So then you can take derivatives with respect to u and v and get this little cross product here, in that formula 3. Now, sometimes if the surface is a graph, if it can be written as a function of two variables, then the formula, the flux formula, reduces to another formula. But again, in general, for finding the flux, let me just see here. I'm looking here. Flux came up in section 13.6, surface integrals. Right. In general, for finding the flux, I like to always use this formula 3 here because it always works. It always works. Now, another thing to keep in mind too, when you use formula 3 and you have your cross product here, okay, the cross product, you have to do the cross product in the right order so that it matches the orientation of the normal vectors, okay, to the surface, whether it's an outward or inward orientation. And we've talked about that a lot. So one thing I'll mention too, Green's, like just for an example, sometimes in problems like for Stokes' theorem, it assumes, like formula 5 here, it assumes outward orientation. But what if you had a problem where the orientation was not outward, but it was downward? What would you do? What would you do? How do you handle that? Let's take an example like Green's theorem. Let me just take another example here. Green's theorem assumes that the particle is moving along a closed path in two-dimensional space, and it's moving counterclockwise. Well, what if your particle is moving clockwise? Okay, how would you adjust Green's theorem then if your particle is moving clockwise? It's a closed path, but the particle is moving in a clockwise direction. How would you adjust Green's theorem so you can get the right answer? What would you do? Good, that's right, Yeva. Put a negative in front of the Green's theorem, in front of your answer. That's right. So, okay, I mean, these kinds of concepts are ones that you've encountered in your homework, but you want to be, you want to be very comfortable with, with the chapter 13 ideas, and before you take your final exam naturally. Was this exercise helpful? How many of you found this helpful? Okay, Yeva likes it. Good. Norina likes it. Matthew, wonderful, wonderful. Christopher, Logan. Okay, well, good. Are there any questions at all before we end the recording? Simons likes it too. Wonderful. Okay, I will go ahead and stop the recording here.